Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from University of Science and Technology of China, Code to World, a GUI world model via renderable code generation. Modern GUI agents can look at a screen, read text, and decide where to click. But compared to humans, they're still surprisingly brittle, especially on long, multi-step tasks. A key difference is that humans mentally simulate what will happen before we tap a button. Agents usually don't. If they click the wrong thing, they may need many steps to recover, or they might trigger irreversible actions like sending money or deleting data. This paper is about giving GUI agents a safe virtual sandbox, a world model that lets them preview the next screen before they commit to an action. There have already been attempts to build world models for GUI agents. Some use text. They describe the next state in language. That captures intent, but throws away the actual visual layout. Others generate pixels directly, often with diffusion models. Those can look realistic, but they struggle to represent the precise, discrete structure of an interface, especially when there's a lot of text. For real GUI navigation, you need both high visual fidelity and fine-grained structural control. Existing text-only or pixel-only approaches can't deliver both at the same time. Code to World takes a different route. Instead of predicting text descriptions or raw pixels, it predicts the underlying code of the interface, like HTML. Given the current screenshot, the user's action, and the goal, it generates structured code for the next screen, then renders that code into an image. Because the representation is code, we get precise control over structure and layout. Because we render it, we still see a realistic screen. In effect, Code to World becomes a learnable virtual sandbox. Agents can ask, if I do this action, what will the next screen look like? And get a concrete visual answer. Formally, the task is next UI prediction. We start from the current screenshot, the user's action, and the overall task goal. The model first predicts the next state as structured HTML code. Then a standard rendering engine turns that code into the predicted next screenshot. This two-step process lets the model approximate the environment's transition function, how the interface changes when you perform a given action. That's exactly what a world model is supposed to learn. To train a code-based world model, you need many examples of screens paired with their underlying code. But popular GUI benchmarks, like Android Control, only give you screenshots and action coordinates, not the actual layout code. So the first big challenge is data. How do we build a large, high-quality dataset that links real mobile screens to faithful HTML-like representations? The authors solve this by synthesizing code from images and then automatically checking and refining it using visual feedback. The authors build a new dataset called Android Code, with over 80,000 screen action pairs. They begin with trajectories from Android Control, which provide real screenshots and user actions. For each screenshot, they prompt GPT-5 to generate structured HTML under strict constraints, including a fixed-size root container, so coordinates line up. They then render this HTML back into an image and compare it to the original using a SIGLIP similarity score. If the score is high enough, they keep the pair. If not, they enter a revision loop. GPT-5 sees the original screenshot, the rendered image, and the current code, and is asked to fix the code based on visual differences. This loop yields a high-fidelity corpus of GUI code, aligned with real screens. To keep the generated code robust and reproducible, the pipeline enforces several constraints. The HTML documents are fully self-contained, no external image URLs or dependencies. Instead, images are represented as gray boxes with short text labels like IMG, avatar. Icons are drawn as simple inline SVGs. This ensures that rendering is deterministic and independent of the network. The visual feedback loop keeps revising any sample whose rendered image doesn't match the original closely enough, targeting a SIGLIP similarity above 0.9. The result is a clean, high-quality dataset that tightly couples visual appearance with structured code. Once the dataset is ready, the next challenge is teaching a vision language model to predict code that actually matches the visual world and respects user actions. The authors start from Qwen 3 VL8B Instruct as the backbone. In stage 1, they do standard supervised fine-tuning. Given the current screen, action, and goal, the model learns to output the ground truth HTML. This teaches syntax and basic layout patterns. But at this point, the model only sees code as text. It doesn't know how that code will look when rendered. Stage 2 fixes that by adding reinforcement learning, where the reward comes from the rendered images and from checking whether the predicted transition makes sense for the given action. In the first stage, the model is trained in a straightforward, supervised way. Each training example includes the current screenshot, the user action, and the task goal as input, and the target HTML code for the next screen as output. The model is optimized to predict the correct code tokens, just like a normal language model. This stage is mainly about learning the structure of HTML and the typical layout patterns of mobile UIs. The vision encoder is kept fixed, so the model leverages its existing visual understanding while focusing its learning capacity on code generation. The second stage makes the model render-aware. For each input, the model samples several candidate HTML outputs. Each candidate is rendered into an image. Then 2 reward signals are computed. The first measures visual semantic fidelity, how well the rendered image matches the ground truth next screen in terms of layout and structure. The second measures action consistency, whether the change from the current screen to the predicted one is a plausible result of the given action. These rewards are estimated using a separate vision language model, acting as a judge. The policy is then updated with group relative policy optimization, which compares candidates within a group and nudges the model toward code that both looks right and behaves logically. Measuring visual similarity for these UIs is tricky, because the generated screens often use placeholders instead of real images. Off-the-shelf embedding metrics like clip or siglip can be overly sensitive to style differences and miss structural details. To get a more meaningful signal, the authors use a vision language model as a judge. It sees the ground truth next screen and the rendered prediction, and is instructed to focus on layout, element positions, and structural correspondence, while ignoring superficial style differences. It outputs a continuous score, RSEM, that reflects how well the predicted screen matches the true one at a semantic and structural level. Visual similarity alone isn't enough. A world model could produce a screen that looks plausible, but doesn't actually reflect the user's action. To enforce correct dynamics, the authors add an action consistency reward. Here, the judge model sees the current screen, the action, and the predicted next screen. It evaluates whether the transition is a reasonable outcome of that action. For example, whether clicking a button opens the right page or scrolling moves content in the correct direction. This yields a second score, R-act, which penalizes hallucinated or illogical transitions. The final reward is a weighted sum of R-sem and R-act. To judge how good a GUI world model really is, the authors propose a dedicated evaluation protocol. It has 2 main dimensions. Functional logic asks, does the predicted next screen follow the interaction rules? This is measured by action adherence, which checks if the transition matches the action, and action identifiability, which asks whether you can infer the action just by comparing the before and after screens. Visual quality asks, how well does the layout and structure match the ground truth? This is captured by element alignment and layout integrity, both again using a VLM as a judge. They also report siglip and Dino scores as more conventional image similarity baselines. The authors evaluate code to world on 2 main benchmarks. Android control serves as the in-domain test. It uses the same device type as training, but with unseen applications. So it checks generalization within a familiar environment. GUI Odyssey is the out-of-distribution benchmark, with different devices and a wide variety of app styles. This tests whether the world model has really learned interaction dynamics, rather than memorizing layouts. They compare code to world against strong image generation models like Gemini 3 Pro Image and GPT Image 1, as well as code generation VLMs like GPT-5, Gemini 3 Flash, Claude 4.5, and several large open-source models. Despite having only 8 billion parameters, Code 2 World performs extremely well. On Android control, it beats all open-source baselines, including models that are more than 10 times larger, across both functional logic and visual quality metrics. It even rivals proprietary giants like GPT-5 and Gemini 3 Pro Image. On the more challenging GUI Odyssey benchmark, all models see some drop in visual similarity, but Code 2 World maintains very strong action adherence and identifiability scores. That suggests it has truly internalized how GUIs respond to actions, not just how they look. Looking at qualitative examples makes the differences clear. Smaller vision language models sometimes fail to change the screen at all, effectively ignoring the action. Larger models may understand that, say, a search bar should appear, but produce messy or incoherent layouts. Pixel-based generators like Gemini 3 Pro Image can produce beautiful images, but they tend to preserve the original layout and struggle to synthesize entirely new pages. Code to World, by contrast, accurately predicts the new page structure, the correct widgets, and even subtle details like the time change in the status bar. This shows that the code-based representation really helps capture both logic and layout. Beyond standalone prediction, the real test is whether Code to World actually helps GUI agents perform better. The nice part is that it's plug and play. You can attach it to many different agents, without retraining them. At inference time, the agent uses code-to-world as a look-ahead simulator. It proposes several candidate actions, simulates the next screen for each one, and then selects the action whose predicted outcome best advances the task. This propose, simulate, select pattern lets the agent spot hallucinated or risky actions before executing them on the real device. Concretely, here's how the loop works. Given the current screen, the task goal, and interaction history, the agent proposes several candidate actions, each with a reasoning trace and a confidence score. For each candidate, code-to-world predicts the next UI by generating HTML and rendering it. A separate scorer, often another VLM, then looks at the goal and the simulated outcomes and decides which action leads to the most promising future state. The system can override the agent's original top choice if the simulation reveals that it would fail or get stuck. This simple pattern significantly improves decision quality. In offline experiments on Android Control High, the focus is on single-step decisions. Given a state and a human-labeled next action, can the agent predict the correct action type and target? The authors plug code-to-world into two different agents, a specialized GUI agent called Mobile Agent v3 and a general-purpose multimodal model, Qwen 2.5 VL7B. In both cases, adding code-to-world improves grounding accuracy and overall success rate. For Qwen 2.5 VL7B, the grounding accuracy jumps by over 5 points, making it competitive with domain-specific agents. Even Mobile Agent v3, which is already strong, benefits from the extra foresight. Offline tests are useful, but they don't capture the full complexity of real interaction. Android World is a live Android environment with 116 tasks across 20 apps, where agents must generate entire action sequences. Here, the authors integrate code-to-world into the default M3A agent framework and test several backbone models, including GPT-4o, Gemini 2.5 Flash, Qwen 3 VL8B, and GLM 4.6V Flash. In every case, adding code-to-world increases the task success rate. For Gemini 2.5 Flash, the improvement is especially striking. Success jumps by 9.5 percentage points. This shows that accurate visual foresight directly translates into better long-horizon navigation. To understand which components really matter, the authors run ablations. Starting from the raw Qwen 3 VL8B, performance on next UI prediction is quite poor. Adding supervised fine-tuning on Android code already gives a big boost in both functional and visual metrics. Adding only the visual semantic reward, RSEM, further improves layout and similarity, but doesn't help logic much and can even encourage reward hacking. Adding only the action consistency reward, RACT, strongly improves dynamic logic, but leaves some visual roughness. The full code-to-world model, which combines SFT with both rewards, achieves the best balance, with top scores across all metrics. The authors also study how world model quality affects downstream performance. They fix Gemini 2.5 Flash as the agent and vary the simulator. With no simulator, the success rate is about 41%. Adding a naive simulator based on the untrained Qwen 3 VL8B barely helps. But as the simulator improves, first with SFT, then with RSEM, then with RACT, the success rate climbs steadily. The full code-to-world model, with both rewards, reaches about 51%, a 9.5-point absolute gain. This tight correlation shows that better next state prediction directly enables better planning and decision-making. This slide highlights the overall code-to-world pipeline. On the left, you see how Android code is built. Constrained initial HTML synthesis from screenshots, followed by a visual feedback revision loop that enforces high alignment. On the right, you see the two-stage training, supervised fine-tuning to learn code generation, and render-aware reinforcement learning with dual rewards to align the model with visual outcomes and action logic. Together, these components turn a generic vision language model into a specialized code-native GUI World Model. Beyond benchmarks, code-to-world has broader implications. On the positive side, better GUI World Models can make agents safer and more capable. They can act as assistive tools for users with disabilities or take over tedious digital tasks, while using the sandbox to avoid dangerous real-world actions. But there are also risks. If the world model hallucinates a safe-looking screen when the real action would be harmful, it could mislead the agent. And like any powerful automation tool, it could be misused for large-scale navigation spam or cyber attacks. The authors emphasize the need for robust verification and responsible deployment. To wrap up, Code-to-World introduces a new way to build GUI world models. By predicting renderable code instead of just text or pixels. The Android code dataset supplies the necessary training signal, with tens of thousands of carefully aligned screen code pairs. Render-aware reinforcement learning, driven by visual semantic and action consistency rewards, turns a generic VLM into a precise simulator of GUI dynamics. And when you plug this simulator into existing agents, you see substantial gains in both offline and online navigation. The core message is that accurate code-native visual foresight can be a powerful lever for safer and more capable GUI agents.